Okay, so which bullet points from the study guide did you want to discuss?
So I was looking at the bullet point that says like how I know it sounds like a very simple question, which I'm assuming is based on the attractions between the two atoms, electron. I just can't think of it right now. It's the question that says, be able to explain how atomic orbitals overlap. That's...
Okay. Be able to explain how atomic orbitals overlap, and that the number of molecular orbitals that results is equal to the number of atomic orbitals overlapping?
Yeah.
Okay, sure. Yeah, let's talk about that a little bit. So, let me bring up, I'll share my screen with you so I can draw some stuff that you can see.
Okay.
Alright, so the only situation where you would need to be able to draw molecular orbitals that result from atomic orbital overlap would be when there are only two atoms involved. So there's a couple scenarios where that where you might be asked to do that. We talked about hydrogen bond in lecture. We talked about the possibility of helium bonding with helium. Might ask you about a carbon-carbon bond. And there's actually two types of carbon-carbon bonds. One is called a sigma bond, and one is called a pi bond. So we can discuss those a little bit as well. So along the lines of that bullet point, as well as some other bullet points that are related, if you're looking at the hydrogen covalent bonded to another hydrogen, in order to make that covalent bond, what has to happen is the hydrogen's nucleus, so I guess I'll just represent with that with a little positive, since there's one proton in the hydrogen's nucleus, would be surrounded by electrons in an orbital. And what type of orbital is that?
Isn't it like an S?
Mm-hmm. Right, hydrogen has its single electron in the 1s. So I'm just going to use a little arrow to represent that single electron spinning up. Not a very good looking arrow. Fix that up a little bit. So we've got one electron in that orbital or cloud. In order to make a bond, the other hydrogen atom would bring its 1s close enough to overlap. And its single electron would also be in its 1s orbital. So one key conceptual note associated with that is anytime two orbitals overlap, they always get converted into molecular orbitals. And the number of orbitals you start with has to be equal to the number of orbitals created. So since I have two total orbitals, two individual 1s orbitals, I have to get two orbitals created.
So isn't that the anti-bonding and the bonding orbitals?
Right. So there's always going to be one that results from constructive interference, and there's always going to be one that results from destructive interference, and that will be bonding and anti-bonding. And so, yeah, you're right. So when, and that is a result of the orbitals in reality being waves. And since waves are described with a mathematical equation that either has a positive sign or a negative sign, if the two waves add with the same sign, they'll add together, and the probability of electrons being in that area of overlap will increase, because the probability of electrons being in a certain area depends on the wave function and the magnitude of the value for that wave function. So the larger it is, the more probability of their electrons being there. So once the nuclei get close enough for the orbitals to overlap in that region, the nuclei are at that same distance, the constructive interference creates a higher probability of electrons being in that area. So now I have one new orbital that kind of takes on a shape where there's even more electron density now in this area than there was, and that's pretty stable because the electrons can be in a position to attract both nuclei at the same time. Conversely, since there's also, since I'm starting with two orbitals, I can't just now suddenly only have one orbital, I still have to have two orbitals. And so the other orbital that's also created, that usually doesn't have electrons in it, it's usually empty, because if I only have two electrons, then they're going to both go in to the orbital that stabilizes them more. But the other orbital would result from destructive interference, and that would be an anti-bonding orbital. So if the positive mathematical value for one wave cancels out the negative mathematical value for the other wave, then there's no wave left in that area, and that's when you get a node. So if there's a node between the nuclei, then the electron density is like on either side of that, and if there were electrons in there, they wouldn't be able to be on the node, and so the two positively charged areas of the protons would repel if there's no electron density in there. But since there are electrons in the bonding molecular orbital and there's no electrons in there, the unstable nature of the anti-bonding molecular orbital doesn't really affect the molecule or make it unstable. Helium would be the same situation, except with helium I would have 4 total electrons, as we said on Thursday. So if I have 4 electrons, well then in that case the bonding molecular orbital and the anti-bonding molecular orbital would both be full, and so the energy advantage of putting 2 electrons in the stable orbital would be canceled by the energy disadvantage of putting the electrons in the unstable orbital, and so there's no net energy advantage or disadvantage to forming a bond between 2 helium atoms. So the entropy greatly disfavors the bond, and that's why the bond doesn't form between 2 helium atoms.
So what about...
Say that again?
So what about like the octets with like how bonding anti-bonding orbitals relate to the octets? Like, because like helium has its noble gas configuration already, so like how does the bonding anti-bonding relate to that?
It relates to it. That's a great question. It relates to it in that typically when an atom has an octet, like for example in this molecule the hydrogens make octets. In this molecule, if the carbon's bonded to other things, the carbon will make octets. Typically when the atom makes octets, at the same time there's just enough electrons shared between the atoms to put all the electrons in bonding molecular orbitals, and all the unstable anti-bonding molecular orbitals are empty, so they're not really making it unstable since they're empty and there's no electrons in them. So that kind of is like an explanation for the octet rule. At least in part it explains why octets or noble gas configurations are stabilizing for atoms, because when atoms bond in a way to make octets or noble gas configurations, it happens to happen when there's just enough electrons to fill up all the stabilized constructive interfering bonding molecular orbitals, but no extra electrons beyond that, so we don't have to put any electrons in the anti-bonding orbitals that would make it unstable.
Okay.
And if you go beyond an octet, Like if you imagine a carbon having like a lone, like 4 bonds and a lone pair, where would that lone pair go? Well, it could go in an anti-bonding molecular orbital, which would make it way less stable. Or you could imagine it going in an orbital in the 3rd energy level that's also empty, but that's also really unstable because there aren't enough protons in the nucleus to attract electrons into the nucleus that would be way far away in the 3rd energy level or in an anti-bonding molecular orbital. So just to complete this, what we're saying here, if in order to make a carbon-carbon sigma bond, what happens is one carbon will have an orbital sticking out into space, and this is going to be usually a hybridized orbital. So if you haven't looked ahead at this yet, we're going to talk about this on Tuesday, so it's not necessarily going to be on the exam coming up, but SP, SP2, or SP3, depending on the carbon. So we'll get more into that on Tuesday. I don't have to worry about that too much right now. But the shape of that orbital is kind of like a lobe sticking out of space. There's another lobe over here, but it's usually small enough and it doesn't overlap with anything, so it's not really significant. Often we leave it out or ignore it. If there's another carbon that has the same situation, then it would overlap its orbital head on with the other carbon, and then again, if I have exactly 2 electrons in that area of overlap, they can go into a bonding molecular orbital versus the antibond. And so what that would look like here is same situation. If the area of overlap causes an addition because they have the same wave sign, then I get constructive interference, and there's an even greater percentage chance that the electrons are in that area between the 2 carbons where they can attract to both carbon nuclei and make it especially stable. But if they cancel because they have opposite wave signs or opposite mathematical formulas for their waves, then just like up here, I would get a node, and the electron density wouldn't be on that area. It would be mostly over here and over here. And so there I have a situation where it's unstable because there's no electrons in the middle to attract the protons, and the protons would get close together and repel. A pi bond is similar, except it's a different type of orbital overlap. And again, we'll talk about this on Tuesday in lecture, so it's not super critical right now, but I just wanted to mention it since we're talking about this orbital overlap, and it's just more examples of the same thing to kind of reiterate the concepts and hopefully make them more clear for you. But in a pi bond, instead of having one of these hybrid orbitals with these shapes overlapping head-on, facing one another, we end up with a situation where if the carbons get close enough and they have an unhybridized p orbital, what's the shape of a p orbital?
Isn't it like the double-lobed figure-8 shape?
Right, so these SP, SP2, and SP3 have a similar shape, but they have one side that's bigger and one side that's smaller. So as you correctly said, the p orbital is more like a figure 8, where the 2 orbitals are similar in size on the top and the bottom, and I know they're not exactly the same, but I intended them to be the same size there. So if one p orbital on one atom overlaps side by side with the p orbital on another atom, then the areas of overlap are kind of like side by side instead of head on. So that's the difference between a sigma bond and a pi bond. But again, it's still the same concept. In the area of overlap, there's both constructive and destructive interference. And related to that bullet points, what we've seen in each one of these examples is I've got 2 orbitals overlapping, whether they be 2 hybridized orbitals or 2 p orbitals, so I have to get 2 new orbitals. I always get constructive interference and destructive interference, both have to form. So in the constructive interference situation where the bond is formed, again, there's a adding together of the wave functions, and so I have an increase in the probability of electrons being in that area, and so that creates a bonding molecular orbital that looks like this, where most of the electron density is here and here, right in the areas of overlap. As you correctly noted, a p orbital has this figure 8 shape because there's a node that splits that in half where there's no electron density. So that node is still there, and now we have electron above and below the plane of the carbons. In the antibond, if the wave functions cancel in the area of overlap, then I create another node. So in that situation, I already have a node here because there's a node in these p orbitals, but a second node is created because of the canceling of the waves if one is positive and the other is negative. So there I kind of get like an orbital, a single orbital with four different sections, and the electron density here is really, again, not close to the nuclei. It's not in the area where it can attract both nuclei, and the nuclei are close together, repelling one another, so that's especially unstable. So if we were to look just real quickly, we've got 1, 2, 3, 4 different orbitals that we could imagine for carbon-carbon bonding. If we were to look at the potential energy of those orbitals, is it correct to say that when I have a high potential energy, the bond is stable or unstable?
Unstable.
Good. So, which of these 4 do you think is highest in energy?
So, be the fourth one?
Good. Yeah, that 4th one is especially unstable because the electrons aren't really around the nuclei, and they're definitely not in the area where they'd be most stable, right between the nuclei where they can attract to all the positive charges. So the potential energy of that orbital will be especially high. Which would be the most stable?
The first one.
Good. So the first one there would be especially stable. And then this one here, this is a bonding molecule. It's relatively stable as well. So then that one would be there, and this one would be here somewhere. So that there is a bullet point on there as well that talks about relating the stability or energy of the electrons to the shape of the orbital.
I'll be right back really quick.
Okay, sure. I'm just gonna
I'm
pause.
sorry.
That's okay. I'm just gonna pause the video. No worries. All right. So the question is, why would electrons be more stable in a bonding molecular orbital? So there's a couple reasons for that. So if we look at these bonding molecular orbitals, what do they have in common versus non-bonding versus anti-bonding, right? So those are 3 situations that we want to keep clear in our minds. So in the bonding molecular orbital, there's a couple advantages. One is the electrons are mostly in the area between the nuclei. So whether it be the sigma bonding molecular orbital, where the electron density increases right between the nuclei, and that's why that's the most stable, because that area of electrons can attract really effectively to both positive charges because it's close to both of them, right? So we know in general the closer opposite charges are, the more stable they are because of the strong attraction they can form to one another. Or the pi bond, where the electrons aren't really right between the nuclei because there's already a node there. They're still just above and below that area, so they can still get pretty close to the positive charge and form some decent attractions there. So that's probably the main one. And that's true versus a non-bonding situation, right? So if we imagine these carbons not bonding together because they're not close enough for their orbitals to overlap, whether it be a sigma or pi situation, if the atoms aren't close enough for their orbitals to overlap, well then the electrons are really only able to attract to one nucleus at a time. right? Because they're only in an orbital around one nucleus. But over here, there's more attractions we can form when the electrons get in an area close to two nuclei instead of just being in an orbital that's just really around one nucleus. So that's versus non-bonding situation. It's mainly the proximity of the electrons to both areas of positive charge and being able to attract to both. The second point, though, is why electrons in bonding molecular orbitals are especially stable compared to anti-bonding. So if we're talking about versus anti-bonding, not only do bonding molecular orbitals have this advantage that we just mentioned, they also have the advantage that, versus an anti-bonding molecule, because in anti-bonding, the nuclei repel one another. Right? So when we look at any of the anti-bonding molecular orbitals, what we see is there's always a node between the nuclei, so there's no electron density in that area, and the positive charge associated with the carbon's nucleus has really no negative in this area. So if there's no negative in that area, those positives are kind of exposed to one another, and that makes it even more unstable. So I know I wrote REPL here by mistake.
I didn't even notice.
But yeah, the nuclei form an extra repulsion that makes it even more unstable than it would be if they weren't even bonding, right? Because if the nuclei aren't even close enough for their orbitals to overlap, then their positive charges aren't really close enough to cause much repulsion, and so the repulsion isn't even an issue there. So that's why the bonding is the most stable, as we talked about, is the most stable, and then the non-bonding is an intermediate level of stability, and then the anti-bonding is the least stable, because the anti-bonding has the extra repulsion in addition to the fact that there's no electrons to form the extra attraction like we get in the bonding compared to the non-bonding situation. What else?
So, I'm sorry, for a second. Okay, so the way how the next bullet point was worded is just kind of funky. Like, I wasn't really able to decipher it out.
This one here?
Yeah, the way how it was worded, it just seems odd.
Yeah, so that's just saying the amounts are equal and that they offset. So what we mean by that is, let me see. Try this here.
Isn't that where, like, the... let me think here for a second. Like, the two... Like, I know what to say, just think of what to say.
Yeah, so let me just show that. So again, if we're looking at potential energy, which relates to how stable it is, recognizing that it's more stable when it's lower potential energy and more unstable when it's higher potential energy. So if we want to compare, that bullet point is really comparing a non-bonding versus bonding versus anti-bonding. And so what that bullet point is saying, and that you should know, is that if the non-bonding situation, where the atoms aren't even close enough yet to overlap their orbitals, has a certain energy, then the bonding molecular orbital that would result from the overlap is going to be more stable by the same amount that the anti-bonding is less stable. So if I were to put electrons in both the bonding, which would make it more stable, and the anti-bonding, if I had electrons in both, then the instability associated with the antibonding would cancel exactly the stability associated with the bonding, and there'd be no energy difference between bonding and non-bonding.
Yeah, I was about to say that something along those lines. It's like I just couldn't even think of it on top of my mind.
Yeah, well, does that make sense?
Yes.
Okay.
Yes.
Yeah. So, I mean, that bullet point doesn't really have much to it in addition to what we already talked about, because we already discussed which ones are more stable and why with these points here. All that bullet point is doing is adding to that the amounts are equal and offsetting. So any instability associated with an antibond is going to be the same quantity, but in the opposite direction from the stability associated with a bond if it's the same type of bond.
Yeah, I was about to say, like, man, this question, like, the way how it was worded, it should have been worded something along the lines more differently.
Yeah, there's probably a better way to phrase that.
Hey, at least I know now. But yeah, lower potential energy, I think that's what should have been put there. Because that way you know what's going on.
Yeah, potential energy would be good to insert there, I agree. Yeah, I could do that.
So I know, I wasn't sure that, the very last bullet point, like, I know, like, it's not really the last part, but, like, the first part of that last bullet point. I know it seems like a simple concept, but I wasn't sure if there was more to expand upon it or not.
Yeah, so this last bullet point here relates to some of the pictures we saw at the end of lecture on Thursday.
Mm-hmm.
So it's definitely not something I can draw. So I'll just go to that section of the textbook so we can talk about those pictures. That was these pictures here. This is a molecular orbital for CH3Br. So what the pictures that we did draw over here are indicating are simple situations where there's only two atoms involved in the bonding, and those are relatively simple because you get these specifically predictable shapes based on the constructive and destructive interference, giving the bonding and anti-bonding molecular orbitals respectively. But once you get to a situation where you have more than two atoms involved, and now the carbon is overlapping orbitals with the hydrogen, it's overlapping orbital with another 1s of another hydrogen and another one, and it's overlapping an atomic orbital with the bromine. All of that overlapping together kind of adds together. It's so I don't have like multiple individual instances of the type of pictures we just showed. Instead, I have all of this kind of overlapping together, creating these larger orbitals that kind of extend over multiple atoms. So I don't expect you to predict the shapes of those or to recognize, where they're going to exist or even where their nodes are going to be, just to know that it's different and to know that when I've got multiple atoms involved, the shapes of the molecular orbitals, I can't just predict those off the top of my head. I need a computer to model those shapes based on the equations that are involved. And then when I get those shapes, I also have to recognize that each one still only represents one orbital, despite the fact that it's covering multiple atoms. So it can at most hold up to 2 electrons because it's still only one orbital, whether that orbital consists of like 2 areas split by 1 node, or whether, like in the next example after that, I'm way too far. Or whether it's an example like this where I have an anti-bonding orbital that has multiple nodes. No matter how many sections one orbital is split into by nodes, it's still one orbital and it can still only hold a maximum of 2 total electrons. But the same general ideas still apply, which are that if the orbital allows the electron density, shown by these red and blue areas, to be between the nuclei, it's going to be able to allow the electrons to form more attractions. It's going to be stable, and that's where electrons will be more likely to reside. This one is called a Lumo because it's unoccupied. The U there stands for unoccupied. It's unoccupied because it's not that stable, because there's lots of nodes in there. So if I give you a question about that, it would just be about, I can't think of an exact way the question might be worded off the top of my head, but what you would need to know is just that once you have more than 2 atoms involved, the orbitals end up being weirdly shaped, and they end up extending over all of the atoms. And when they do, it's still only an individual orbital can still only hold 2 electrons, and the electrons will still, in the ground state at least, go into the orbitals that allow them to attract to the most nuclei at the same time.
So basically all I need to say is just get a handy dandy computer calculator and you're good to go.
Well, that's what you would need to do to get the shapes of the orbitals. That's true,
Okay. Okay, that makes a lot more sense now.
Excellent.
Now this is concerning the wave sign.
Mm-hmm.
Like in the bullet point says wave sign, how wave sign squared gives the shapes of the orbitals. Like where does the wave sign square come from?
That's just that's part of the mathematics that's involved. So the wave sign is a mathematical equation. I'm sorry, not the wave sign, the wave function. So you could say wave or wave function. If you say wave or if you say wave function, then you're referring to this mathematical equation. Anytime we're looking at any of these orbital shapes, whether it be a large molecular orbital extending over multiple atoms, or whether it be a small molecular orbital that results from just 2 atoms overlapping their atomic orbitals, the shapes of all of those orbitals come from taking the wave function equation and squaring it and then plotting that in 3 dimensions, and that's where you get these weirdly shaped plots. So that's not obviously anything you need to do. As we said, that's something a computer would do, but the wave equations that physicists have worked out end up being squared, and then when those equations are squared and plotted in 3 dimensions, that's where you get the shapes of these orbitals. That's pretty much all you need to know about that.
Alright. And I think there might be one last thing.
Sure.
So, why is there an optimal length for each covalent bond? Because I know if you stretch it out a certain extent, it will become unstable. If you compress it a certain extent, it will become unstable as well. I wasn't sure if that was a good reasoning or not, but...
So there's a little bit more depth to the reasoning than that, but that's definitely a good start. So we talked about that back here in the beginning of the chapter here. So when we talked about that, we said, let's grab this here. Alright, so for this explanation, whatever the covalent bond is, as we said, there's some optimal distance. So if you stretch the bond and make it longer, you're decreasing the orbital overlap, right? So when we saw what's the advantage of bonding at all? Why do hydrogens even bond? Well, the answer is, as we said, because they'll form a molecular orbital where the electrons will be able to primarily be in the area of the atomic orbital overlap, so they can attract to both nuclei at the same time. So if I start to stretch the bond, instead of getting the hydrogens at the correct distance, so so that their 1s orbitals can overlap a lot. If I stretch the bond and make it a little bit longer, well, then I have a situation where maybe the hydrogens overlap a little bit, and if there's only a little bit of overlap, then the molecular orbital that would result would only have a little bit of an increase in electron density in the area where the electrons most effectively attract the nuclei. So there isn't as much of an energy advantage, or it's not as stable, or it's not as low in energy if I have less effective overlap between the atomic orbitals that are used to make the molecular orbital. So that explains why if you stretch a bond, it's not as stable, because once the hydrogens get far enough apart, their orbitals don't overlap at all. The electrons can only attract to one nucleus at a time. And even in the process of getting farther apart, if their orbital overlap doesn't really happen much, then you don't get much of an increase in electron density in that area. So the electrons basically are just attracting to their individual nuclei instead of getting in the area of overlap and attracting to both.
I will be right back.
Sure, that's okay.
I feel so bad.
That's for why the energy increases when you stretch the bond?
Yeah.
Okay, so then for compressing the bond, as we were saying, if the hydrogens are at the optimal distance, we get nice orbital overlap. Electron density increases due to the constructive interference in the bonding molecular orbital, so electrons go in that orbital and get in that area to attract both atoms at the same time. If you compress the bond, in the case of hydrogen specifically, it becomes unstable because the nuclei get too close. And so even if there's orbital overlap and the electrons are in that area, if you bring the nuclei too close together, then the opposite charge repulsion is going to make it less stable. And that shoots up really fast, because once you push them too close, that repulsion becomes really significant. And the closer you go, it just jumps way up and becomes really unstable.
So do the electrons repel from each other as well as the nuclei from one another?
In the case of hydrogen, not really, because there's only 2 electrons total in the whole structure, and those electrons are just going to be in here attracting to the protons, just like they would for the most part when the hydrogens are at the optimal distance. But if you looked at something like carbon, where carbon has lots of electrons, including the 1s core electrons in both nuclei, well then if you try to make a molecular orbital around that, if the carbon nuclei get too close, then not only will their nuclei start to repel their positive charges, but then also the core layers of electrons that are not involved in the bonding and are only around one carbon at a time, they can start to get too close, and then the electrons of the core electrons of one carbon repel the core electrons of another, and that also makes it really unstable as well. So really, for any element pretty much other than hydrogen, there's going to be multiple layers of electrons, and when the nuclei get too close, the core layers of electrons start to get too close, and that does cause a massive repulsion, and that is more of a factor in that instance than the nuclei getting too close, unless they get really close.
Okay, got it.
Great questions.
I think that's about it, hopefully.
Yeah, well, we haven't covered too much, so I think hopefully this will work out well. We're taking our exams on smaller bits of material, so people don't have to focus on so much all at once. I'm really optimistic about how things are going to go. I'm hoping people do real well, and I'm thankful that Diana suggested we record this so that maybe other people will benefit from it. But in general, if you do have other questions come up at any time, feel free to reach out.
Alright, will do. And thank you.
You're welcome, Amy. I'll talk to you later.
Alright, you too.
All right, have a good night. Bye.